Hello and welcome to this class on quantum mechanics and quantum computation. In this video, I'll give you an overview of this subject and the class. So, quantum computation is built on this remarkable discovery that quantum systems are exponentially powerful. So what does this mean? Well, roughly, you could say that a system of 500 particles, its computing power can be as large as 2 to the 500. Okay, so let's try to understand what this might possibly mean. So if you could exploit this computing power which was as large as 2 to the 500, how big would this be and how could you possibly match it classically? Well, classically the way you might try to compute quickly is by either increasing the speed of your computation of your computer or by using parallelism, by having many computers working in parallel. Well, how much parallelism could you have? Well, it turns out that 2 to the 500 is much larger than the number of particles in the universe. And that's, by any stretch of the imagination, an upper bound on the amount of parallelism you could possibly have. 2 to the 500 is also larger than the age of the universe in femtoseconds. So, well, that's by any stretch of the imagination the fastest you could make a computer run and the longest you could make it run. In fact, 2 to the 500 is much larger than the product of these two numbers. And so if we could possibly exploit this latent computing power in quantum mechanics, this would give us an unimaginably fast computer. And this is the starting point of quantum computation. Now, of course, it's not as simple as this, because we have to work hard to channel this power towards solving computational problems. Okay? And to do this, we have to be able to pick the right computational problems to solve on a quantum computer, and then we have to design the right kinds of quantum algorithms. So let me give you an example of this. Factoring, which is probably the most famous example. So factoring is the problem of given n as input, decomposing it as a product of prime powers, p1 to the e1, p2 to the e2, pk to the ek. So for example, you might be given as input the number n equal to 60, and the factoring problem says find its prime factors, so you might write it as 2 squared times 3 times 5. Okay? This is a problem that's notoriously hard for classical computers. So hard that its hardness is used as the basis for the RSA cryptosystem. This is the cryptosystem you use to send your credit card number every time you make an online purchase. Okay, so, well, that's the correct kind of problem. Now, what about the correct kind of algorithm? Well, for factoring, there's this famous quantum algorithm due to Peter Shor, which factors integers in polynomial time. What this means is that quantum computers, if we could build them, would break RSA cryptosystems, the RSA cryptosystem. In fact, there are quantum algorithms that would break most of modern public key cryptosystems. Okay, but now one has to be careful, because this exponential computing power that's latent in quantum systems, in order to exploit it, you have to start with the right kind of computational problem with the right kind of structure. not every problem has this structure. Now, you wouldn't know this if you only relied on the popular media. So even as publications as respected as The Economist are extremely optimistic when it comes to the power of quantum computers, and they regularly make this mistake of believing that you can solve all kinds of problems exponentially faster on a quantum computer. So one of the things that we'll do in this class, in addition to understanding how to design quantum algorithms, such as the algorithm for factoring, is to understand what are the limitations of quantum computers. Okay, now, in order to design these quantum algorithms, we must understand the basic principles of quantum mechanics. And one aspect of quantum mechanics, a striking aspect, is that it's a very counterintuitive theory. In fact, the famous physicist Niels Bohr said, anyone who is not shocked by quantum mechanics has not understood it. Okay, so quantum computing exploits the most counterintuitive aspects of quantum mechanics. So in this course, in order to understand how to design quantum algorithms, we are going to have to learn these basic principles, which are extremely counterintuitive. And so another way of looking at this course is that it provides a very simple introduction to basic quantum mechanics. And the reason we'll be able to provide this this simple introduction is we are going to use very simple building blocks, which is qubits or quantum bits. These are the basic building blocks of quantum algorithms, and quantum gates. This approach to learning basic quantum mechanics actually emphasizes the paradoxes, the counterintuitive aspects that are at the basis of quantum mechanics. And it also, by putting it up front, it gives you a chance to actually start developing a new kind of intuition for quantum mechanics. It also has the advantage of being more concrete and hopefully more fun.